Hello, guys. Welcome to CyBRICS 2021 task analysis session. Sorry for the delay. We were setting everything up so that it doesn't break. This is day one. It's Tuesday and Wednesday will be day two. And we are joined today by Mikhail Dragunov and Alexander Menshikov, who are the two task authors that will tell us about their tasks today. So today will be like some webs, some CTB tasks, and I think today will be the day of the easy tasks. And tomorrow we'll cover some pawns, some hard forensics, hard network, and stuff. So to begin, first of all, thanks for playing CyBRICS. As always, I hope you enjoyed our 24-hour adventure for you. Let's congratulate the winners. So the first place came to Super Gessa from all over the world, an alliance team. I think they originate from Korea, but that's not 100% info. Second place, WNM from China mainland. Third place, Bolson, the famous team from Taiwan. And we have honorable mentions, of course. Fourth place, CatBitSet from Russia. Fifth place is ECSC Team France from France. We're going to cover the challenges that you guys have voted the most at the Google forum for the task analysis. By the way, if you want to get a certificate that you took part in CyBRICS and took some place, you can still fill in this form. And I think next week, the university will issue some certificates for you. So, one of the most voted challenges for the write-up session for task analysis was, of course, web hard Checkin, which had 0 solutions during the game, like the hard forensics. So it won the popular vote. Well, it tied, but it was the most voted challenge in the forum, together with one more challenge. So let's start with web hard Checkin. I know you are waiting for some write-ups for task analysis, but unfortunately, we need to apologize. We screwed up. We screwed up in a major way. The challenge was unsolvable as presented at the contest. To tell you more about it, I'm handing it over to Mikhail Dragunov.
Yeah. The idea behind the task was that you need to decrypt the data inside ASCII code using bit flipping and padding oracle. Then you'll have to encrypt it back, but include your blind XSS payload. Sadly, there was an error in implementation. Initializing vector for crypto was hard-coded, and it was practically impossible to solve the task because without knowing the initializing vector, you cannot fully forge the plain text, and you always stuck with 16 bytes of random data. It would not be a problem if not for JSON parser that expects valid UTF-8 everywhere. So you need to brute force initializing vector somehow, or try to brute force random data that will be passed through that JSON parser. But chances of that are very low, like 1 in 500,000, and it would not be a problem again if not for the ASCII encoding and decoding, which taking a lot of time and making that brute force thing impossible in the time frame of our competition. To our best knowledge, the standings were not affected by this issue, but we're still very sorry for this screw up and would like to apologize for stealing your time with this challenge. So we're not going to show you the solution for this task right now, but we'll propose something instead. We have fixed this challenge. Now we use the standard encryption scheme with random IV prepended to ciphertext. The first 3 teams who successfully solve this challenge will get a $100 Amazon gift card from us as an apology, or an equivalent in your country that you choose. The same announcement has been made in the CyBRICS chat, so be sure to tell your teammates who might be interested, especially if they were close to solving this task at the game. Vlad?
Here he is. Okay, thank you. And once again, we're very sorry about making an unsolvable challenge. That's too bad. And I hope you just finish the challenge and claim your bonus that you prepared. So let's continue with another challenge. And surprisingly, one of the most voted challenges, and actually having got the same number of votes as the web hard Checkin, was the CTB Baby rf'er. So let's quickly get it through rf'er. So what do we have here? We have some SSH account, which we are going to log into now. I'm going to make font larger. Let's go. The legend is we had a shell on some box, and accidentally we did rmrf all the files from root folder. So now we don't have any comments. We deleted all the binaries. ID doesn't work. Your name doesn't work. What else? ls, tier, and stuff. So there is no external comments. And it's pretty common challenge for CTFs. Everyone knows how to read files using bash. So when you have a bash shell, you can make this one a read, some variable name v, and redirect the std in from the file. And yeah, you got yourself a line from the file read. So both read and echo are bash built-ins, so they are not, they do not require any binaries present on the system, just your shell session. But if we try read here, it turns out there is no read because it's not bash. We could fingerprint the shell from the messages, or just look at the errors which say it's TC shell, TCSH. So let me show you the same equivalent technique for TCSH. Actually, I just was sifting through random shells and Googled how to read a line from a file with TCSH, and it turned out TCSH has a magic pseudo variable or something, which is called dollar and input, which substitutes for a line input from std input. See? We actually can do something like this: echo this pseudo variable and redirect from the file we want to read. By the way, we haven't still found the file that we want to read. We have no ls, but just as in bash, file path expansion works. So we can make something like echo asterisk, and we get the listing of root folder, echo slash etc. slash asterisk. We got listing of etc. We have something called etc. CTF, etc. CTF asterisk. All right, here we have the flag. So we need to read this file. But if we just write this, like echo the variable and redirect from flag.txt, it still reads from std input. I solved it like this. I just wrapped it in a subshell. So if we wrap it in a subshell, this thing actually reads from file instead of the keyboard. And here's the flag we have read from the flag.txt. I saw someone, well, actually, I saw many teams using another built-in of TCSH called source to try and read the file. And the source is the built-in that loads commands from some file and executes them. And if we use source, we see that congrats, command not found. And actually, there are some. I don't remember how to see the help for the built-in, but there are some flags for the source command that allow to keep the lines of the file in your command history. So I think it's -h, and then history. Yeah, history shows us that apparently the file only contains congrats, but we already know that's not the case, and that's because of just these hash signs at the beginning of the line with flag. So the shell treats them as comments, and it doesn't land into history. So here is how I solved the CTB Baby. The intended solution was this one. I wonder if there were some unintended ones. Oh yeah, actually I know about one unintended solution. So actually, when we connect the SSH, under the hood, it spawns a Docker container with Ubuntu and does rmrf everything just live. So now we don't have comments, but we can spam, I think, Control-C or something. Let's try spamming Control-C. No, Control-C just, I think, kills the Docker. Let's spam Control-Z. Okay, we spammed Control-Z, and we actually interrupted the process of removing all the files and binaries. So now we have all the binaries, we have ls, we have not removed any files from etc. So CTF, the full listing, cat. So here is the real contents of the flag.txt. And yeah, the entire root folder, well, not the entire, but the most of the root folder is intact. So this one was an unexpected solution. By the way, I haven't told you yet, but you can actually ask questions in the YouTube chat. So we will look at the chat from time to time and answer your questions. Jeremy ASMG tells us that ls -f works. Well, it does work, but it doesn't do any like extra stuff, because ls -f is also a TCSH built-in, and it just emulates the ls -f, just like that. And well, it doesn't give any more info than echo asterisk. So yeah, that's that. The next one, like logically, that I want to show you is CTB Medium, which is RM escaper. RM escaper offers us to escape the Docker inside the same task as CTB Baby. So we run a new task container in Docker every time you log in over SSH. And we need to, instead of capturing the flag from the container, which we already did, capture the flag from the host system itself. And now we are not given any extra info. So let's just see what we have on the container itself. Actually, I'm going to spam Ctrl-Z. So I'm getting the fully fledged shell. Here is the script that removes everything from the root folder. Here is the Docker file. Well, nothing interesting. Ubuntu and TCSH. Okay, here is the run.sh. This is the file that's being run as you log in into the over SSH into your account. And there are a couple of comments here about this setup, how to make the challenge work. And we see that the user rf'er that we are giving the password to is being added to group Docker. Well, it's logical because rf'er should be able to start Docker containers. But what group Docker does is actually one simple thing. It gives access to the Docker socket. I'm now switched to my local shell. I've got Docker running. Here is the Docker socket, and we see that the only group that has access to the Docker socket is group Docker. So when you want to give your users access to Docker containers, you add them to group Docker. We are in the group Docker. So this command works because it uses the socket. And actually, we can abuse that. We can abuse that over SSH by utilizing Unix socket forwarding. We write -L as when we would want to forward just a TCP port, but instead of TCP ports, we write a Unix socket path. This one is the local path, Docker 2, for example, and this one is the remote path. Let's try forwarding. All right, let's check out what is now in the var run. Docker2.sock. Okay, now let's use the Docker command of the Docker client, and I think it's -H, Unix, and then the path to the socket. So now our Docker client will contact the Docker over the second socket that we are forwarding to the remote machine over SSH. Let's try. All right, it worked. We got the listing of running containers, which is one container running TCSH now. And classically, we can abuse Docker to get access to the host system. Let's execute on Docker run, rm, ti, net host. Let's mount the volume with root file system into host folder, and let's run Debian, run bash in Debian. So this image is being pulled remotely at the remote system. We are just getting everything over the SSH forwarded Docker socket. Actually, I could use Ubuntu because Ubuntu is the basis of the CTB10 image. But, well, yeah, we can also download some new image. Okay, we got the host name. Now, let's go to the host folder. And here is the lead flag. We have successfully escaped the container and obtained access to the host folder. By the way, this challenge was not was not random. Actually, we had exactly this vulnerability at the previous year CyBRICS setup. So fortunately, nobody has thought about it and found it. But like half a year later, I realized that we could just forward the Docker socket over SSH and escape to the main CyBRICS server, which is kind of bad. So that's all for the rf'er and escaper. Let's look at the YouTube chat. What do we have here? Okay, Jeremy SMG asks, for the players, is this a Docker inside the Docker? Yes, actually. When you connect to the port, when you connect to the port 22, behind the scenes, like a lot is happening, but behind the scenes, a new Docker container is spawned with Docker in Docker. I think it's called Docker dint rootless or something. So Docker in Docker allows you to run Docker inside the container. So everyone who connects to that port gets a fresh container. And of course, inside the Docker in Docker, we spawn the CTB10, which is the TCSH. So even if the players break out to the real host, they could not harm anyone because they do not share environment with anyone. Alrighty. So the next task will be, let's see, CTB Easy, Lil Buggy Editor, and Mikhail Dragunov will tell you about this task. Here is Mikhail.
Let's see. Hey, I'm stuck with the stupid Buggy text editor. I already quit Vim. I realized how terrible Nano, but what is this? I can't even read the file from the parent directory. Wait. Let's help each other. I show you how to read my favorite book, which is book.txt, and you show me how to read the flag from etc flag.txt. And we are given credentials to connect to SSH and ELF binary. Let's first look at the deployment. And we have some text editor. We can try to open something like book.txt, I think. Oh, I cannot delete anything. Okay. And let's reconnect. Oh. Yep. There's some book. Okay, let's look at the binary. I have already downloaded it to my virtual machine. Let's use totally free copy of IDA Pro. What do we see? some main function, some global buffer, some positions. We have functions like read file, which apparently reads files, print screen, open file, save file, write file. Okay, looks like it is with a file editor. What interesting we can see here? Like in a print screen function, we see that there's some value global buffer that when line prints calculates with this formula. And we need to actually read a file with flag, etc flag.txt. And in the function read file name, there are some checks. Like that, for example, that checks that we cannot make two dots be adjacent to each other. And we cannot write dot slash something to get etc flag.txt. And also, also special symbols not in range of that check, so we cannot write slash. And we need to somehow bypass these checks. And how can we do it? To understand this, we need to look at a global buffer variable that is relatively big, but not indefinite. It's a global variable, and after it we have some space, and after that space we have file name. That maybe a hint for you that there is a overflow involved. In fact, this function. In fact, this formula can be overflowed if our terminal window size is more than 500 lines. So let's try to exploit it. To exploit it, we have mobixterm. Let's write something like something like this to see when we are overflowed. And let's zoom out our console and watch for the string to appear somewhere in the terminal. Actually, we didn't see anything right now because my console window was too wide, and program seg folded because the J was too far from main memory of the process. Let's try again. I'm writing two E's and two F's for the string to be the same size. So I would not overwrite a line terminator or something like this. Okay, let's zoom out. And it's not there. Let's try to use magnifier to show you that there are some strings. It's our file name that we have written. Okay. Now I'll carefully put the cursor down to that string and overwrite it directly with /etc/flag.txt. We need to be very careful here. Okay, looks like I've done it. So let's hit F5. Yep, and we see some text up top. Let's zoom in again. I've hit F5 to reload file. And file name was changed with overflow, and we see it flagged. Okay, do we have any comments, questions in YouTube chat?
Let me check. Nope, not yet. So the next challenge to be written up is CTB Baby, which is Namecheck by Alexander Menshikov. Alexander, I invite you to the Zoom stage.
Yeah. Hello, everyone. Today I will write up some of my tasks. I believe, I hope it was fun for you to solve them, and we'll start from forensics 10. So, we've got the home folder from a criminal's computer. Try to find his or her real name. So we have a tar key archive, and we can unpack it to a folder. I've already done this and opened this folder in like text editor, or you can open it in some another software. Actually, there are 4 files. The .profile, which is not so interesting and quite standard. bashrc, which also looks not suspicious. Bash history file, which tells us something like Instagram. Maybe someone tries to push some filters, commits to his Git repository. And SSH, open SSH private key without public key. So what do we have actually? We have 2 files that we don't need. We have some ideas that Instagram is somehow connected to this task, or maybe not. And we have SSH private key. Well, if we Google for OpenSSH private key format or specification, we came out with the idea that maybe there is something connected to comments or something else. So let's try to unpack this SSH key. Let's maybe try to start this very naive way. Just remove /n and remove these files to get a base64 encoded string. And I will zoom for a little bit. And let's just decode this base64 string with base64 minus d. So we see that this is actually a private key, and there is a comment in the end of this key, which is vivid koala and localhost. Probably that's a username of this criminal. We also can get this information with the built-in OpenSSH keygen command, which have a special key. As I remember, that's -y, which produces a public key from a private key. So we can use, let me zoom for it. And yeah, it allows us to read private OpenSSH format file and produce public key. Let's do this. We can go to this folder. Yeah. Where is the key, and use SSH keygen -f key -y and get public key from a private key. And you can see that this public key, which is usual format for public key format, has a comment in here. So what to do next? The idea is try to Google for this username. We can use some software, some online software like Namecheck or other, or just Google for vivid koala, which is quite a rare name for this guy. But let's remember that we have something about Instagram, so it needs at least Checkin. Let's try to open Instagram /vivid koala. Yeah. And we see an Instagram profile of some guy. And today there is no stories because the story was deleted 24 hours after the competition. But during the competition, there was a story which looked like that. Like this. So there was a ticket, a boarding pass, which doesn't include username or middle name or first name, anything. But we know that usually in boarding passes, there is a code which probably includes some additional information which was not censored. So we can just copy this from the screen and go to some, by the way, that's not difficult to Google. That's a PDF 417, as I remember, barcode, which is quite standard. And we can go to decoder, PDF 6417, and just try the first one. I believe most of them can decode this image. So let's take the image from the story, and it will be decoded to the boarding pass data. And you can see that boarding pass data includes first and second name of this guy, which is Divov Nikolai. The only trick that you probably expected is that on different devices, Instagram can not produce the full-sized image. So probably if you go to this Instagram from, I don't know, from maybe smartphone with a small screen, probably you will get a minified image which is difficult to decode with barcodes. So in this case, you probably need to Google for Instagram get full-sized image online, something like this, and take like one of these online services to extract the full image size story. So to come up, what probably you need to do is unpack target.gz, read bash history, decode OpenSSH private key, find Instagram profile, find ticket image and stories, and decode this barcode getting a real username. Well, that's it.
Alrighty. Thanks for the write-up. And we have a question from the YouTube chat. Dmitry Tatarov asks, why did you choose the message Instagram filter? It exists in the GitHub commits, in the GitHub commits, and it interfered with the solution.
Well, yeah, but what exact repository on GitHub will you find? So
I actually think, well, we did not create a GitHub, right? For this challenge.
No,
I think someone else did.
I knew one of the players asked me if this SSH key is from GitHub, so probably someone registered with this private key on GitHub.
Okay.
And it's possible to SSH on the github.com with this private key, and you will get a profile name of that guy. But as I remember, that his profile was almost empty.
Interesting. Dmitry Tatarov says it's about 6 months old, meaning, I guess, the Instagram filter commit. Well, that was probably a sly metagame by some team to backdate the commits and stuff. Well, maybe we'll check what GitHub account has been created. Alrighty.
Yeah, I think there is a very common string. It should be almost everywhere.
Okay, so that was Forensics Baby. And the next challenge will be Network Baby, ASCII Terminal by Artur Hanov. We do not have Artur just right now with us over Zoom, so we're going to roll a recording. Enjoy.
Task ASCII art terminal, ASCII terminal, and this task was intended to show you some interesting idea when you get output from terminal in ASCII art and can give comments to terminal also in ASCII art. Your commands execute in bash. Here it calls bash and sends input from user input here. Of course, to do this, we must implement two functions. First, convert text to ASCII art, and second, convert ASCII art to text. When we need to convert text to ASCII art, we call this function. What does it do? It just creates a new image, and this image has a text label in white background. This text label was drawn in Arial font, and after that it converts this image to ASCII art. It may be done very easy. Here we just iterate all pixels in image and converts it to ASCII art by this rule. If we have black pixel, then it will be this symbol. If we have white pixel, it will be this symbol. And if we have gray pixel, we have some of these symbols. After that, it prints to user, and user can enter his ASCII art line. So here we read input from user and get this input and trying to recognize this. Here it calls this function. This function tries to convert user lines to some text. How we do this? At first it creates some image with white background, and after that it prints chars to this image by the reverse rule. It means that if user entered this symbol, it prints black. If user entered this symbol, it prints white. And for the rest symbols, it prints some grayscale. After that, you have not ASCII art image, but just a pixel image. And this image sends to PyTesseract. PyTesseract tries to recognize this and return line. This line will be executed in this function, and of course its output will be converted to ASCII art and returned to user. So to solve this task, you must create some ASCII art which just executes your commands. For this task it was easy, and flag was right in file system. Let's look at how you can find this. Let me go to terminal, and here I have several already prepared images. For example, this. Just ls command. Let's try to send it to our server. We sent ls, and it failed to recognize this. Yes, it did. ID. Good. ID just returned us some ASCII art, yes, and so we need to look at this. How can we do this? Forward it to output text. And let's look at this. To make it more clear, set no wrap. And now we see here that it just returned as a result of ID count. flag was located at the same file in flag.txt. You may find this from ls command, but this command now may not be recognized by Tesseract. So to recognize this, we may just try to modify this text file to make it more clear for Tesseract. Not clear. Okay. For this comment, I already wrote some program which may create ASCII art for different comments. It was this file. It just contains source code of the service with just functions of converting some argument to ASCII art. Here I used free mono, which recognizes by Tesseract better. So this file just prints me comment in ASCII art. This comment was this. It just cut flag.txt. Let's try to do this. It was recognized good, but at the end of this, it also recognized some strange symbol, but it didn't miss comment. Okay, let's forward it to out. And look at out. Set no wrap. And now we can see flag, CyBRICS and so on. So it probably was difficult to create ASCII art which may be recognized by Tesseract.
Alrighty, thanks virtual Artur. That was Network 10 ASCII terminal. And the next challenge will be Web Easy announcement by Alexander Menshikov. Let's go.
Well, I hope you see my screen. So one moment according to the previous task. As I mentioned, we can take this SSH private key and just SSH to the GitHub itself using this key. It can be done with with SSH-E. That's the name of the private key, and GitHub.com. This line just to trick my SSH agent. And when we try to log into the GitHub via SSH with this key, we can see the username of someone who added this private key to his settings on GitHub. But if we see for this guy on the GitHub, we can see that he's joined during the competition and his profile is quite empty. So, well, that's it. And let's move forward to the next task. Announcement. Ladies and gentlemen, allow us to introduce a brand new project, the flag. Let's go to this website and see nice website with the form where we can enter some email. It just prints us this email and says that they will contact us. Okay, let's open inspect panel and move forward to right and open network console and try to see what's going on if we send notification. We can see that it just sends request with email that we entered and some digest which looks like MD5 of this email. It's easy to check, just go to the page source, see the script.js, and you can check that it just adds digest of email value, which is MD5 of email. So we can probably try to send something else, which is not email, to bypass the client-side verification. So let's use curl, something like announcement. You can craft something like this, just send post data with, oh no, that's, let's go to Python itself. So let's write simple script which just sends post request to the announcement website and add post params. The first one is email, the second one is digest, which is MD5 of the payload itself. If we run like add single quote and run this program, we will see what happens. So Python demo py, and it will print us the HTML code of a response. And you can see, let me zoom this a little bit. I just copy this string to the editor. So we can see that there is a MySQL error which tells us that the syntax is bad. So from this error message, we can think that there was something like insert into some table, values, some values, I don't know which, and here goes an email which we inputted and some timestamp which is null. So probably we can use just a simple SQL injection attack with the only moment that it happens inside insert. So we need to somehow extract this information from insert query. There can be some several methods how to do this. The most simple is error-based SQL injection, which can give us some additional information via this error message. Let's add, for example, I don't know, just plus database, which is a standard function which returns us the name of the SQL database. And let's run this example one more time. Yeah. So we need play a little bit with types of these messages. The usual approach is to try maybe to add different types of data. Am I running the demo? And see what happens. Yeah, probably we need to fix this request to be valid. Yeah. Let's try without hex. Yeah, this is it. What have we done? As I mentioned previously, there's something like insert into values, something else. There goes our email data and now. So instead of this string, we can send something like this to make this query actually valid, but invalid because there are different types of input data. So from the error message, we can see that it's truncated, incorrect double value announcement, which is probably the name of the database. We can do even maybe subquery inside this, like try to select 1, 2, 3, 4. And we can see the same error message. No, there is no error message. We just see this as an email. But it can be select database or so. It shows us the name of the database. And then we can use the standard technique to go to information schema and try to extract all databases, all tables, and all columns that are inside this database. I will show you PHPMyAdmin with the structure of this database. You can see that there is an emails table with 3 columns and logs table with actual flag in log column. So there are many emails, about 200,000, no, 100,000 emails that you send during the competition. And I just show you how probably you can solve this by hands without using some utils. So the same code, that's just for simplification, I just extracted the answer from the error message by splitting it before and after parts of the string. And then there are some usual and typical for SQL injection strings. Select database, select table name from tables where table schema is announcement, select columns from table name logs, and so on. If we run this script, you can see that it shows us the name of the column, the name of the table, and actual data inside the logs. So probably this is it. To sum up, just find digest technique, send single quote, use SQL injection in insert, and get flag from information schema from logs. That's it.
Alrighty. Classical SQL injection. We have a question in the YouTube chat. SDF asks, can we see the backend? I think it's about the backend for this challenge.
You can. This is it.
Yeah, I think it's pretty straightforward.
Yeah, there is a stupid mistake which probably make this happen, because there is firstly insert into and then getting email for showing the message. And it is queried by ID, which is last inserted ID. So probably if there was not such a text and we just pass email from the user to the message, this technique won't happen. But why not? Probably it will happen because it's error based. So yeah.
Okay, great. So SDF says thanks. And the next challenge will be, let me see, easy reverse engineering, which is kernel reverse by Artur. And once again, let's roll Artur's recording.
Task IOCTL driver. This task was intended to verify that you are able to reverse Linux drivers and write application with IOCTL interface. In Linux, we have different ways to interact with the driver. More common ways are interacting with block devices, interacting with some files, and one interesting way is IOCTL. What does it mean? Let me open the source code of driver. IOCTL interface.c is the main part of such driver. Here we look at the main function in this driver. It is IOCTL interface. This interface is intended to send some buffer to driver with a specific command number. Command passes in CMD integer and buffer passes in arg number, arg reference. After that, IOCTL verifies the value in CMD, and if it equal to specific values, it calls some handlers. So we have now two handlers, set flag and get flag. Set flag intended to copy flag from user space to driver space, and of course it must be called only from root user. So here I verify that UID of current thread, which called this interface function, it verifies that it equals to 0. If so, it continues to copy value to flag from argument. In another case, it prints error. So after that, you need to get flag from kernel, because this flag copies to static variable which lies inside kernel space. You cannot read this from user account. So you must interact with driver. Here you may call IOCTL with get flag number. To solve this task, you must solve some challenge. This challenge just a simple reverse. You must reverse this function and find that a driver reads some value from user buffer. User buffer is here. It reads some value to value. Value is unsigned integer. After that, driver reads value from get time of day function, value number of seconds, and XORs number of seconds with this number, this constant. It XORs this with this constant and verifies that user passed the same value in value variable in arguments. If so, it copies flag to user buffer. So you need to reverse this driver. Let's look at solution. Here is my solution. First two functions are open and close driver. It just opens and closes driver by specific path def. And in main function it sets flag and gets flag. Of course, at start of system I insert driver in kernel and calls this program. This program just sets flag in kernel and after that gets flag from kernel, verifies that we are able to get flag to solve the solution. So this program also is also a solution, but of course you are not able to set flag from user account, but you are able to get flag from user account. Let's look at solution. At first, I already installed driver in kernel. If we look at this, ls mod grep ioctl. Good. Also, we have device in dev. Good. And here is my solution. It inserts flag in kernel, and now it prints a value from kernel. It is this print. Let's look at IDA. Here we see a function which handles IOCTL calls. At first, optimizer made some strange optimization, but of course it doesn't have structures which was returned from current task, and so we just can see offsets. So it's not clear from this that it just verifies that we are root or not root. But the main part of this driver challenge, it is here, and it is more clear. We see here that we read some time value and XOR this value with specific value, with constant. After that, it returns flag, copies flag buffer to user, or returns no. So to solve this task, you must write application which calls IOCTL with this constant in CMD and with some value which depends from current number of seconds. This value may be obtained from getTimeOfDay function.
Alrighty, great. The next challenge will be Web Medium Multichat by Alexander Menshikov.
Yeah. So another chat messenger with room support, free to use. So our task is to convince the admin to give us a flag. Here is a tip. Admin and some kind of tech support guy are members of a secret chat room. And this guy can ask admin to tell him the flag if he writes him a message. Hey, I forgot the flag. Can you remind me? And then admin will tell him the flag. So let's investigate this chat. Here we can see some random room number generator and chat. Actually, we can investigate how the authentication is happening. If we see to the storage, we can see that the room number is just saved in a non-secure cookie. So that's kind of typical, but let's think what we can do here. Probably let's join this chat from another window. We know the room number, which is this. Let's try to just join this chat with WSCAT, which is WebSocket CURL alternative. Let's write header, which is cookie, and room equals to this number. -C tells to connect to this WWS URL. You can easily see this URL with how to see page source, and in page source, here is JavaScript source of this task, and you can see that it just connects to the WebSocket and prints messages. And the room number is practically impossible to guess. So let's connect and write some messages to yourself. You can see that, yeah, hello, we can chat with yourself. Well, what else we can see? We can see that there is a support form where we can give probably that support tech guy some URL, description, and Checkin, which is probably for stop brute forcing of this task. Checkin we can take from the task description. It's here. And URL, let's place something that we controlled. It can be your server, or it can be some public server. I recommend webhook.site, which gives you an easy way to copy a unique URL and see who accessed this URL. Let's paste in here, press send, and see if someone will go here. And someone was on our server. That's some not interesting guy with Firefox browser. So probably we need to somehow get his cookies. You can see that WebSockets are involved in here. And actually, in normal situation, we couldn't do anything because cross-domain requests are usually blocked by the browser itself, but not for WebSockets. This attack calls something like WebSocket hijack cross-domain. Let's Google for it. And there is cross-site WebSocket hijacking, the name of this attack. So the idea is simple. Browser, I don't know why, but it sends cookies with cross-domain WebSocket requests. That's not for all browsers. I could prototype this task for the latest Firefox. Unfortunately, it's only been done with the latest Firefox in Linux. With latest Firefox on macOS, I couldn't make this works right. That's why I decided to use not latest version, but a little bit outdated version of the browser, which works in every operation system. To do your prototype and experiment with this on your laptop, for example. So how it works? Let's craft a simple HTML like this, like shown on the slide. Simple JavaScript, which connects to this URL, and on open, it will send the message, hey, I forgot the flag. And on reply, it will forward this message to our site so we can see the response. Let's write a simple Flask application, or you can use some online tools. I don't know. It looks like this. It just hosts, that's a Flask application that just hosts our HTML JavaScript code. So let's run this file and let's copy this URL to that guy. Let's imitate that guy. We can open inspect panel. Let's open network panel and see what happens if we go to this URL. You can see that it creates a WebSocket connection. And it actually sends cookies during this connection. And if we go to our chat in other, oh, I closed it. But it's open in here. You can see that we've got this message, so it works. And in the webhook side, we can see, oh, here is another link. Let's paste here a valid link, which is slightly different. So probably it will work with the guy from the tech support if it works in our browser. Yeah, looks legit. And let's send this URL to the tech support. And don't forget to get a new team token. All right, something's happening. And yeah, here is the flag. CyBRICS bound cross-site WebSocket hijacking. Well, kind of, that's it.
Great, great. Okay. The next challenge will be by Mikhail. It's Forensic Easy called Recording.
Yeah. The description is simple. I found a strange recording. What does it hide? When we click, we download file strangerecording.mrf. And first we need to know what type of file it is. So we Google mrf. Well, we see that some mouse recorder file from Bartels Media. We go to bartelsmedia.com and we don't see mouse recorder here, but we see similar software, which is a macro recorder. Okay. We can download it. Okay. It is already installed in my virtual machine. It doesn't require a license or anything. And we can open this file with it. What do we see? We see a lot of mouse moves, clicks, and other things. We see that Firefox.exe was opened in pastebin, with pastebin in it with some locked paste. And we see that osk.exe, which is the Windows on-screen keyboard, was used. So we can try to replay it. Something is trying to happen, but we can open Firefox. We can open screen keyboard. And try to replay it again and see what happens. Okay, we see that something is happening in the area of on-screen keyboard. but clicks are not working, and on-screen keyboard is misaligned. So what we can try? We can try to limit what we are playing. For example, turn off Windows changes. So it won't try to find Firefox window. And we can use some graphic editor like paint.net. We can change the size of our canvas to like something like this. Zoom in. Select brush to make it, for example, red. Make its width bigger and add a new layer. Yep. And let's see what we can achieve. Okay, we can stop right now and oh, it was unexpected. It stopped. Delete last actions that were done occasionally. We can take a screenshot of an on-screen keyboard, then paste it as a new layer. Close on-screen keyboard. Copy just the on-screen keyboard, paste it at the new layer, delete the previous layer, and now we can try to align on-screen keyboard with key presses. So we know that pastebin.com was used, and using this knowledge, we can align the on-screen keyboard with image in graphic editor. So it would cover those presses. Okay. Okay, maybe it was a bit wider. Oh, yeah. Or maybe looks like it was something like this. Yep. Looks plausible. Now we can clear that layer with drawings and try to replay recording again. Okay. Yep, I found the problem. Okay, we start again. Now we need to select the right tool and play. Okay, that was PA, and we need to stop it now again because I moved canvas and it is misaligned now. I moved it again. So we need to do this. I think we need to crop canvas a bit to prevent further issues with moving canvas. Okay, and let it be here. Select by a brush and play. Okay, we have our PA, and we need to expand canvas now a bit. Like to pixels, and we need to move on screen keyboard. Okay. Select mesh, and we can start playing again. P A S T E B I N dot C O M slash U Z Q Shift. So it's capital C J capital U, capital F, then capital U, and A. Okay, let's try to open and see whether that paste exists. I assume that you recorded it in some notepad by hand, for example. Okay, it's a locked paste. So we are on the right track. Now let's maybe delete everything that was almost everything that was before opening of paste bin window. Look at this cool animation. Okay, we see that actions counter is decrementing because I hit delete and it is deleted now. So now we assume that the user who recorded this was also recording password for paste bin locked paste. And now with less actions, let's try to see what happens. Okay, it's 9, Y, capital D, Z, 5, I, capital Z, P, R, and D. So that's it. Now let's try to unlock this paste. Okay, I will write here. 9, 5, I, capital Z, P, R, D, and unlock, and we have our flag. CyBRICS macro rules. Okay.
Yay!
Do we have any questions?
Let's check. Genrich Wellman говорит, I think the better way is size screen keyboard as in Paint, then turn on macros. I didn't actually
doesn't
understand.
work. No, it doesn't work because.
Oh, you mean like launch the on-screen keyboard and make the real keyboard the same size?
I think he means that, yeah.
Mm-hmm.
But it doesn't work because that macro recording can't change context to press buttons on the on-screen keyboard because it uses some Windows things to be always on top on everything, and because of it, a macro program can't do its tricks there.
Oh, strange.
Understand what's happening. Yes.
By the way, maybe it only applies to Windows 7 because on Windows 10, it actually could interact with the on-screen keyboard.
Oh, really?
Yeah. And actually, this recording was done in Windows 10. Okay. And it's lucky that Windows 7's on-screen keyboard actually also matched the pattern of the keys. Oh, okay, so anyway, thanks, Mikhail. And the next challenge will be my challenge, which is rebyC Medium Pngoshop. Surprisingly, the rebyC Medium got only one solution. So let's dive right in. We get a netcat APN port and some ELF binary, which is probably listening on that port. I have already downloaded the ELF. And for example, let's check out what we have on the port. And on the port, we have some secure image editor, which tells us the information about the loaded picture. And we can do some things like toggle byte order between MSB, LSB, toggle secure mode between disabled and enabled, load some image, download image, and edit it. So what do we have here? We can load some predetermined list of PNGs. For example, capture. Okay, we have loaded capture, which is 400 by 100 pixels. We can download it, and it spits it out as base64. We can edit it, which is an entirely separate menu. We can resize the image, flip it horizontally and vertically, add grain to it, black and white, and colorful inverted colors, and that's it. So, first, let's play a bit with the editor. I think I'll have to quickly link. No, never mind. I'll just work in the shared folder. So, let's try, for example, to log every line that's being output to a file. It will be useful later. Let's quickly load, for example, capture and download the image. The log allowed us to keep that base64. And let's quit and see what we have downloaded from the server. Let's load it in, and on base64, this chunk of data. Base64, we see there is a PNG. Let's save it as lol.png. And when we view it, it's the capture from another challenge. Okay. I remember there was some flags in the preloaded images, flag.png. Let's load the flag and download it, right? Download image, but no, it says we can't download the flag in non-secure mode. Okay, let's enable the secure mode. Secure mode enabled. Let's download flag this time and see what we have in the log. So now what we have in the log is I already see that it doesn't start with if 0r, which is base64 encoded PNG. So probably that's some binary trash. Let's check it. And yeah, it indeed is some binary trash. And in secure mode, we have one more chunk of data. Detached one-time pad. Okay. And it doesn't show us anything. Let's check that it does show us something in the if we load something else that than the file, than the flag. For example, painting. Enable secure mode and download the painting. Let's check what we have. Again, some random trash. Here was the ending. Okay, not a PNG at all. And we have detached one-time pad. Now it's visible because it's not the flag. Let's write it to a file too. otp.bin, for example. And well, we can either reverse the binary. I haven't actually yet showed you the binary. Or we can just use the common sense that one-time pad is like XOR cipher. You XOR the 120K of the picture with 120K of the random bytes, and that's your encryption. But let's actually verify that. So I just quickly renamed all the functions, all the variables, so that we don't waste time on the reversing. And let's check out what download does. First, it renders the PNG. And PNG is getting landed into PNG data array. There was some, okay. There was some hotkey to add line feeds. Well, okay, but is there undo? Yes, now there's undo in either. So yeah, we fill the PNG data array with the PNG data. Then, if we swap the endianness, then PNG data, all the bytes in PNG data get flipped. Then, if we have an environment variable of unsecured debug file, we just write the PNG data to the file specified in this environment variable. The environment variable is not set on the server, so it's just to simplify local debugging, so that we can just see easily, easily write a PNG of what we have been downloaded. Then it checks whether we have the flag loaded, and if it's the flag and it's in non-secure mode, it just bails out. If it's not a flag or we have secure mode enabled, it proceeds in giving us the picture. And first of all, when we have secure mode enabled, it encrypts the data. So how does it do it? It allocates the same amount of data as the PNG data length. It uses syscall getRandom to fill the buffer with that PNG length. So get that many random bytes, for example, 120K, and it XORs the PNG data, the data of the picture, with our OTP random bytes. There is no there is no repetitions in the key. It's just a block of random data, length of the as the entire file. Then either a secure mode or unsecure mode, we base64 encode the PNG data, we output the base64, and then if we were in secure mode, we output the one-time pad. So we just do the same thing. We just base64 the one-time pad and output it to the screen. The values that we were XORing the PNG data. But if the file loaded was the flag, we do not get the one-time pad. So we get the trashed PNG data and not the random bytes using which we can untrash it. Let's verify that we can untrash the, what do we have downloaded? Painting, right? Let's verify that we can untrash it. So, well, I prefer PHP. Let's just write to painted.png, lol.png XORed with otp.bin. And indeed, yeah, we decrypted the painting. We have the great PNG file. It's totally valid, totally decrypted. So now we kind of know how the binary works. So now let's get to attacking it. Before doing that, we also need to play a bit with some editing, just to get used to it. So let's, for example, load the same painting. Let's edit the painting. For example, let's resize it to, I don't know, 200 by 400, for example. Then let's invert the colors and let's add some black and white gray to it with intensity. The intensity, if we reverse the binary, is measured in percents, for example, 20% intensity. And let's download the image. and quickly see what we got. I was not entering the secure mode, so we do not need to XOR it. We just get the PNG. And what's the result? Okay, this is the result. We see the black and white grain, we see the inverted colors, and the resize. All right, so the attack. Hopefully there were no binary bugs, so you couldn't just pawn the binary. And the main thing about the unsecurity of this challenge lies in this function, getRandom, which is used to generate the one-time pad. Let's check out its manual page. So it just obtains a series of random bytes from urandom source, and urandom is an unpredictable source, so it's a fair one-time pad, which is not crackable. But if we scroll somewhere lower, we see that urandom source, so the getRandom syscall call, returns a maximum of 32 megabytes of data. And it's a pretty big number, getting 32 megabytes of random trash, but our program doesn't check if getRandom returned enough data to encrypt the entire PNG. If we somehow make the PNG more than 32 megabytes, then the one-time pad will be not filled entirely. And the PNG will be only encrypted in its first 32 megabytes. And the remaining parts will be intact. Let's try to enlarge our PNG in more than 32 megabytes and see what will happen. I think we'll experiment locally. So let's copy. Let's experiment in enlarging our PNG. We need pics. Okay, it worked. And we need some picture to put in pics. For example, the painting, but we'll name it flag so that we get the same behavior. So let's load the flag. Oh, by the way, there is this handy debug environment variable, unsecure debug file, for example, debug.png. So let's load the flag. For example, edit it to resize to 2000 by 1000. Invert the colors. Download to. Okay, can download flag in unsecure mode. Does it write the debug? Yes. So yeah, we will not enable the secure mode to not spam our terminal. It will just write the debug picture. Yeah, okay, we got an image of 2000 by 1000, but now it's only 200 kilobytes. Our goal is to make it more than 32 megabytes. Let's do it like this. Let's resize it to a maximum dimensions. The maximum dimensions are reversible, so edit, resize, and we see the maximum dimensions are 4000 by 8K. Okay, let's do 4K by 8K. We have it resized. Let's again download the image. The rendering part takes some time now. And oh my god, PNG compresses really well. It's only 367 kilobytes. It's huge. It's distorted, but it's not enough by a large margin. Let's actually prevent PNG from compressing so well. We can add noise. We can add grain with intensity like I don't know, like 70%. What this does is randomizes each pixel, and random data compresses very badly. Let's download that. The rendering process should be much more computationally intensive now. Let's wait. And once we have it rendered, let's check. All right, that's what I'm talking about. 100 megabytes. So now the picture with our noise takes 100 megabytes. If we zoom in, we see the noise, but we also see that we can clearly determine the features of the image. So if we exploit this with the flag should be readable. Now let's try to, by the way, am I logging to log? No, I don't think I'm logging to log. Let me restart. So let's try to exploit it using the secure mode so that we can check that we are getting a non-encrypted portion of the file. Let's restart it. T to log again. Load flag. Edit. Resize to 8K. No, 4K by 8K. Add color gray. Wait while it adds the grain. Enable secure mode. And download the image. Let's wait until it renders. And the expected behavior would be to get, encrypting, to get random trash in the beginning and a readable ending, readable footer of the PNG file. Okay, it will take a moment. Alrighty, we have downloaded it. Let's decode the base64. I'll just delete everything except base64. Where does it end? Okay. Decoding the base64. And what we have? We have, in the beginning, random trash. And then we've got the IN signature, which is the ending chunk of the PNG file. Great. It looks like our exploit has worked. Let's try to find the IDAT signature. IDAT chunks are in the PNG file, like the image is split into chunks. They're all compressed, but every, I think, 8 kilobytes of the PNG in my case, in the case of libpng library, they will be a new IDAT chunk. Yes, and we are seeing that here is the helpful histogram of the found results. We are seeing that in the beginning of the file we have no IDAT chunks, and in the end of the file, after exactly 32 megabytes, we begin having the plain text IDAT chunks. So it's a win, but we don't have the first 32 megabytes, right? That's bad. But we can actually utilize the... Oh my god, no. It tries to synchronize the clipboard into the VM. Okay, it's going to take a while. Let me copy something. Oh no, I can't even copy something. Let's copy something like from here. It captured the keyboard. Okay, let's copy something to the keyboard to clear it. And to get the encrypted, to get the plain text of the encrypted beginning of the PNG file, we can actually leverage this thing. Remember endianness? If we set the endianness to big endian, the PNG data just gets flipped. So we can download the entire PNG normally and get encrypted beginning. And then we can flip the NDNS, then download the entire PNG with flipped NDNS, and we'll get encrypted footer and plain text header. So I actually have some, I think, script that solves it. Let me bring it up to not waste time on coding it. 1 second. It was rebyC 200. Okay. Here it is. Solve.py. Let's again bring it up. And here is what it does. First, it loads the flag. Then it edits the flag, resizes it to 400 by 800, 4K by 8K. It adds the colorful grain with intensity of 30. Then it downloads, well, it enables the secure mode. It downloads the first incarnation of the file. Saves it as imgdata1. This incarnation will have the first 32 megabytes encrypted. Then it flips the bitness. It flips the endianness, the byte order, and again downloads the file. This incarnation will have, it also has the first 32 megabytes encrypted, but those first 32 megabytes represent the tail of the PNG image. And then it just takes first half from imgdata2 and second half from imgdata1. So just utilizes the two halves that are not encrypted and writes it to img.png. Running this script takes a while to render the 100 megabytes picture, download it. Maybe it takes 2 minutes. And here is the img.png that it has sped out on the server. Let me load it. It's heavily distorted, but actually we can utilize Microsoft Paint, for example. Here it is, and let's, for fun, squish it in Microsoft Paint. Whoop! Great! Here is the flag. So, get random, returning only 32 megabytes. Who might think? Only one team solved the challenge. Well, congratulations to the team. That's all for the Pngoshop. And the last challenge for today. Oh, wait. Do we have any? No, we don't have. We don't have any questions in the YouTube chat. If you have any questions, you still have time to ask them in the chat. And I'm handing it to Alexander Menshikov once again for CTB Medium to the moon. Where it is? Here it is. Alexander, it's yours.
Okay, so the last task, and it's crypto. So from the description, we see that there is a life on the planet, moon rover, so some picture was taken, but unfortunately strange radio interference occurred. So scientists proved that the message were transmitted with the error rate less than 1 bit flip over 15 bytes of data. And we have software which adds error correction codes, and we have an encrypted and probably interferent message that we can download. So let's download this GPG image and let's examine this source code. By the way, we have an encryption key which is super fast. So let's try to understand what's going on. So we have encrypted GPG image. We have source code on Python, which adds error correction hemming codes and encrypts data with IS-CBC encryption. We also have IS decryption key, which is superpass, and we have information that there were some errors during data transmission. So let's quickly examine what's going on with the encryption. So here are some hemming encryption encoding, which we can quickly examine on Wikipedia. We can see that there are some codes, which is 120 to 127. And there is a mode called SecDet, which adds additional parity, but never mind. Let's continue. So probably there are some functions that can add redundant bits, which allows us to fix some transmission errors. So the main function, it just opens image from the moon rover. It pad the last block with 0 bytes. Then it encodes data as binary. It adds a hemming encode for each 15 bytes block, and finish with encryption of the whole data with IS-CBC. You see that, let's see the example. I prepared some schemes of what's going on. So what happened? We have some data which were separated in 15 bytes blocks, and the last block that was padded with zeros. Then this data were added with some error correction codes. How error correction codes work? It takes 15 bytes of data, which is 120 bits of data. So actual data is 120 bits. Then it adds 7 special bits that will help us to restore 1-bit flip per block. They look like these white rectangles. And the last bit, which number is 128, that's a parity bit. So, according to the Wikipedia, we can see that this encoding allows us to detect and correct one single error. And because of additional parity bits, it allows us to detect but not correct if there were 2-bit flips, 2 binary errors. So, after this encoding, there was IS-CBC encryption with 16 bytes blocks, as usual. Then occurred some random interference, and it produces our image that we've been given. Well, some teams expected that errors occurred not over ciphertext, but over plain text. That's not easy, but that's possible to verify that it's not, that can't happen. Because there are guaranteed by scientists that there can be only one error per 16 bytes of data. So per 16 bytes of data, there may be not more than 2 errors. For example, it can look like this. From this picture, it's easily to see that with the error rate of 15 bytes, of one bit flip per 15 bytes, that's impossible to generate 2 errors in 2 neighbor blocks of 16-byte block. Because even if there are 2 errors per this block, this can theoretically happen, but practically then we can, the next block will have only 1 error. So what will be with correction codes? If there are no errors, the correction code will be 0 and parity bit match. If there is one error, the parity bit mismatch, because if the error will be in actual data, parity bit mismatch, or if this error was in parity bit itself, it won't match. And if there are two errors, the correction code will be non-zero and parity bit will match. If we calculate these blocks over plain text, we can easily see that there are lots of blocks with two errors in neighbor blocks. So it cannot happen. That's why it's logical to see that the radio interference occurred over the transmitted container, over encrypted data. So let's see what could happen. That's the scheme of ASCII decryption. We can see that if there is a 1-bit flip in ciphertext in block, imagine that there is only 1-bit flip, only one error in one block. Then this block after decryption will be completely trashy because of IS incorrect. But the next block will have the same bit flip over plain text because of this XOR. So if we go from right to the left and find this block, by error correction code, we can restore this bit flip, we can flip this bit, and now we know that this bit was actually flipped on the previous block in the ciphertext. So we can flip this bit in the ciphertext and redecrypt the block. If there are 3 blocks in a row, we will just repeat this process. So after we will redecrypt this block, if this plain text will have errors, then we can flip the error bit, XOR this bit in the ciphertext of the previous block, and continue this situation. Actually, if you calculate the situations with parity bit, you can easily spot that there are no situations with 2 errors in one block. So image can be correctly decrypted without errors, because we only can correct 1-bit flip, not 2-bit flips, but we can detect if there are 2-bit flips. So I will publish the exploit code because it's not actually difficult, but it have about 100 lines. So if we quickly go through this exploit, we can see that we just take this transmitted file, get IV, get ciphertext, decrypt it, and then we will, oh no, that is correct, yeah. Then we decrypt it, and then we go through all the blocks and try to remove redundancy of these blocks. And also we can calculate the situations when there are 2 errors, which were shown in the example. Then after we've done with this, we can go from right to the left and just try to find if there is an error in the block. If it's not, we just left this block as valid. If there is a correction, it needs correction. We firstly check if there is a situation with 2-bit flips. Luckily, it's not. And then we just flip the bit which needs correction and save this result after removing redundant bits. And then we need just to find the previous block, which number is I-1, and re-decrypt it with IS after bit flip, of course. That's it. So if we go from right to the left and decrypt the image, it will look like this. So probably this is it.
Alrighty. Great. So I think that was the final task for today. Let's look at the YouTube chat to see if we got any questions or comments. I think we didn't have any. So thank you guys. Thank you, Alexander. Thank you, Mikhail. And thank you, Arthur. Let's check if we have all the guys here. Oh, yeah. Yeah, great. All the familiar faces. So, it's a wrap on the day one of CyBRICS 2021 task analysis session. Please remember that the challenge of Checkin web hard has been fixed. And currently there is a bounty assigned to this challenge. The first 3 teams who manage to solve the challenge, the fixed version, will get a $100 Amazon certificate or whichever is more appropriate for you in your country. So yeah, if you think you were close to Checkin at the game, please, I think that would be interesting to you. Thanks, guys. Please return tomorrow. Tomorrow we'll cover the other half of the most voted challenges, like Pawn, etc., network. And I think that's it. Thank you once again, and goodbye.